All right, we're starting on chapter 10, which is on two sample hypothesis tests. So let's think about what we've done up to this point. So by that I mostly mean chapter 9, which was one sample hypothesis testing. So we had one population with a mean and standard deviation. We took a sample, and then we calculated our point estimate for the mean, which was x bar. And then we performed a hypothesis test. So with this one sample, from this one population, we perform a one sample hypothesis test. That is what we did in chapter 9. We compared this x bar against some hypothesized value for the population. And we drew inferences about that. So one population, one sample to do a hypothesis test. But now we're moving on to two sample hypothesis tests. So we're going to be sampling from two different populations and perform a two sample test. And now we're interested in the difference between the two independent samples. So we're going to be interested in the difference in means between the two independent samples. So to visualize this, so we've got population 1. So we represent that here with this circle, population 1. We take that sample and we get an estimate for x bar 1. And it is sampled from a population which has a mean, which we'll call mu1, and standard deviation, which we'll call sigma 1. We're going to compare that to population 2. And it also has its own mean, population mean, mu2, and standard deviation, sigma 2. We're going to take a sample from this second population, we'll call this sample 2, and then we're going to get an estimate for the mean, which will be x bar 2. So we've got these two different populations, we're taking a sample from each population and getting that point estimate x bar from each sample. So our hypotheses will look something like this, or our hypotheses. So our null hypothesis, our null hypothesis will be that the difference in means will be equal to some hypothesized value. So D naught just means hypothesized value. Typically, this will just be equal to 0. So we could think about rewriting this as mu1 is equal to mu2, because what we're saying is that the difference between them is equal to 0. And in this case, our alternative hypothesis is that mu1 minus mu2 is not equal to this difference, or 0. So another way of writing this is that we think mu1 is not equal to mu2. And this would be, of course, a two-sided test, right? We just think that they are different from one another. We don't know which one's bigger. We're just saying they are different from one another. And then, of course, if we're doing a two-sided or a one-sided test, we might think that mu1 is bigger than mu2. And so if we take the difference, this will be bigger than some value. So we could, again, we could take D naught to be 0. We could rewrite this as mu1 bigger than mu2. Or we might think that mu1 is less than mu2, and so if we take the difference, it's going to be less than some value. Again, if we take that to be 0, we could rewrite this as mu1 less than mu2. So we can do it either way, right? We can write it, we can write the difference as, we could say mu1 minus mu2 is equal to 0, or we could just simply write mu1 is equal to mu2, whatever you prefer to write. Okay, so I'm just reiterating here that D naught is just the hypothesized difference. It could be anything. Typically, we just take it to be 0. We're generally just going to say D naught is equal to 0. But if we actually thought that the difference was equal to some non-zero value, we could do that. We could test that as well. So we could say we think that the difference between mu1 and mu2 is, say, 5. So we might write mu1 minus mu2 is equal to 5. That's up to us, and that's the problem, but for the sake of this class, you can really just replace d naught here with 0. Okay, so we're going to need to make some assumptions to do two sample hypothesis tests for the difference in means. So let's discuss assumptions here. The first is that we need independent random samples from the two populations. All that means is that it's going to look something like this. So here, let me use a different color. By independent samples, we just mean we've got a sample over here, or a population over here, and a population over here. They're two separate entities, two different populations, and we are taking a random sample from each of those populations. That's all we mean by independent random samples. So if this is violated, we're going to use what's called a paired differences. So if they're dependent populations, and we'll talk about that later, but for now, we're just talking about sampling from two separate populations. Okay, the second is that the populations should be normally distributed. So we can verify this by whether, let's say both samples are large. By that we mean N1, so the sample size from the first, or yeah, the sample size of the first sample is bigger than 30, and the sample size from the second sample is bigger than 30. Well, then we know we can just use the central limit theorem, which states that if we have a large sample, then the distribution of the sample averages will be approximately normally distributed. Or we could just simply look at our data. We could create some plots. So we could look closely to see if it's normally distributed. Think about making, for example, a histogram. If we make a histogram of our sample, we would just look, okay, does this look about normally distributed? Right? If we made a histogram, of course, we're just looking for something that resembles somewhat of a bell curve. And then finally, we need to assume the variances are equal. So that is sigma 1 squared is equal to sigma 2 squared. And we're just going to use a rule of thumb. We're going to say what we'll do is we'll take our sample standard deviations, or rather our sample variances, S1 squared and S2 squared, and we'll just take the ratio. So whichever one is bigger, we'll put on top. So let's assume S1 is bigger. So we'll do S1 squared over S2 squared. And if it's between 1/2 and 2, then we'll assume that they are equal. Otherwise, we'll assume they are unequal. And at the end of this chapter, we'll actually form like a formal statistical test to test for equal variances. And what we're going to do is if we see that the variances are equal, let's say the variances are equal, then what we're going to do is pool the variances. But if the variances are unequal, then we're going to use an unpooled variance. This is what these variances are going to come from the test statistics when we're doing hypothesis testing. Now note we can always use unpooled variances. In fact, we're rarely going to use pooled variances. So what we're going to do is we're going to focus more on this case, but I will also introduce this case just so that we've seen everything before. Okay. So throughout the rest of these videos for chapter 10, we're going to work through a lot of different iterations of this. So we're going to start with independent samples. And then we'll see what does it look like if we have unequal variances. And then we'll look at what happens if we have equal variances. And then we'll actually look at some dependent samples, and we'll do a paired differences test. And then we'll finally look at a difference in two proportions. And that's the outline for the rest of this chapter.